dear distinguished scholars of the Carl Friedrich von Weizsäcker-Zentrum, to begin, dear colleagues, ladies and gentlemen, I would like first to thank Dr. Thomas Piecha and Director of Professor Reinhard Karl for inviting me to provide a talk at your excellent center, and to Professor Klaus Meiser, the President of the European Academy of Science and Arts, for arranging this talk. I briefly will introduce the subject of archaeometry, or the new term we initiate in our academy, STEMAC, which means science, technology. Just a moment, because it's not. Can you see it? Can you see it?
Yes, I can see it. And
yes.
The slides are also changing.
Okay. Archaeometry, which sometimes they call it STEMAC. It's a new term that we try to introduce in our academy, which means science, technology, engineering, mathematics in arts and cultures. The best place, as all we know, for finding the past, and studying the past, is not other than an archaeological site, and of course any preserved remains, well-preserved remains of architectural remains and other. An archaeological site is a site where the past activity is preserved and it is traced by various things like food remains, structures, humanly manufactured objects, and others. Invasive, destructive or non-destructive, not invasive investigation of artwork is applied by laboratory and portable instrumentation. The archaeometry or STEMAC provides answers to several questions concerning the material culture. I would divide the wide archaeometry subject into 7 categories: chronology, characterization, bioarchaeology, conservation, archaeoastronomy, ArchaeoGeophysical Prospection, and 3D reconstruction. In particular, archaeometry or archaeological sciences give answers to questions of where, prospection, for example, to locate buried antiquities, to when, how, when for dating, how, why, mobility, ancestry, and past human activity, societies. In any case, whatever measurement is taken, the precision and accuracy, the reliability and proper statistical model are indispensable condition for the reliability of any final answer. Therefore, errors and comprehension of any measurement are essential parameters in the final result. These 2 axioms, axiom 1 and axiom 2, are the ultimate aim of any result. Archaeometry, in fact, relates to a variety of subjects, scientific subjects and problems concerning the past societies, the environment they lived, as it is shown here. For example, with concerning migration, diet, analysis and provenance, protection and prevention, dating, management, technology, science, etc., which ultimately, most of them are related to the blue ovals with a red color around, which is the archaeometry. So the ancient relics, the ancient remains, investigating the past, as I said, requires materials, remains of material culture, the tangible culture, and human artifacts, and man-made constructions, geoarchaeological materials, and human remains of organic and inorganic origin. And also, for all these investigations, one needs instrumentation. Multiple techniques are available to support instrumental analysis, including nuclear, spectroscopy, chemical, and electronic devices. An example of these advanced techniques, for example, I could put, the secondary ion mass spectrometry, SIMS, which can be used to profile cations versus hydrogen and other cations versus depth in obsidian tools, and help to determination of the chronology of the date of construction from the raw obsidian rock made from cooled lava in volcanic centers. Examples of exploitation may include also 5 issues, which I shortly present in the following slide. The implementation of computer systems with the documentation, multimedia digitalization, localization of cultural monuments, enhancements of archaeometric results. The implementation, the first one, of computer systems in the field of culture concerns the popular research and applications of computer systems. The cyber archaeology, as it is called, that has been emerged last decade or so, making use of big data collection, storage, documentation, processing of in the field by various techniques and diversified equipment, with a result the digital reconstruction of monuments and artifacts in the field and in the museums. B is the documentation of museum objects. This documentation is emerging, is an emerging field with fast development, especially for the preservation of at-risk antiquities from natural and anthropogenic destructions. Also, the documentation of the techniques used to make a work of art in a non-destructive, without sampling, readings of electromagnetic rays in the optical, IR, UV, near IR, and beyond, by presenting energy spectra, as for example here, and a kind of tomography, which microtomography, I would say, which digitally reveals underlying layers of, for example, overpainted work of art like a palimpsest. Also, the 3D reconstruction, synthesis, and piece sticking parts of monuments and artifacts produces interesting educational and research data, occasionally insightful. If I try to show you an example here. This is the treasure of Athenians in the sanctuary of Delphi, which has been reconstructed by colleagues from the Coastal Carolina University in America. Really insightful, this kind of works. And this is the table, the omphalos at Delphi, well-known omphalos in the museum, which is under study with my colleagues from San Diego University, trying to find out about these battles, around the omphalos, and really some interesting results emerged from that, which will be shown in public in due course. Also, augmented reality has changed the perception of an object, and in a most accessible and effective manner through our cell phones and tablets. This technology, for example, allows live viewing of a natural environment and whose reality is augmented by looking at the information and images through a computer. This is achieved by computer-generated sensory, such as sound, video, graphic, GPS, etc. This is an example of augmented reality in Tholos of Delphi. And here also is another example of a digital reconstruction from remaining pillars, you can see here on the left, of the Temple of Hera in Metapodium in South Italy, Magna Graecia. also 3D virtual reality and augmented reality of ancient ruins and artifacts. The other subfield of archaeometry is the geophysical prospection. The main objective of the archaeogeophysical prospection is the development and evaluation of application-oriented integrative tools for archaeological interpretation of prospection data. Buried antiquities are revealed through various archaeogeophysical methods. Here are examples of identified subterranean structures as archaeological targets, presented in either in a gray, grading scale or with false color and pseudo colors. And subsequent excavation, for example, here reveals the architectural relics. Here in the geophysical prospection also, which is like X-ray tomography, okay, of underground, proper software development provides not only 2D but 3D mapping, where the resistivity changes implies a target to be excavated. Here, the tomb of A, as we call it in the excavation of Kastruli, the settlement, late Mycenaean settlement near Delphi in southern Greece, where this resistivity changes, the electrical resistivity changes, implies a target to be excavated. Here, the tomb A of the late Mycenaean settlement, you can see here it is the tomb exactly in the settlement, and here is the 3D tomb area, and here again the tomb you can see with red here. As well as electrical resistivity tomography, which is below here, with 2 traverses. This is very interesting and recently published, actually, 2022. Cross-traverse profiles that indicate the limestone basin of a possible ancient marsh or lake. And we have several elements to interpret, and to prove that there was outside the Kastruli, you can see the route here, around 100 meters above the plain here, there was a lake, a small lake, and we have evidence of sinkholes made intentionally by those people, to drain the plain for several reasons: cultivation, for avoiding, diseases, etc. It was a very interesting application. So let me, for all these things anyway, the result has a social dimension, has an educational dimension, and increase the interest and address the market, if I could use the word, of sustainability through the cultural tourism, the supports cultural diplomacy, and triggers the development of new methods and techniques on interdisciplinary manner. Some new advances I'll try to make, shortly. There are so many applications of various archaeometric techniques, which cannot be exhausted, of course, in 30-40 minutes. Only a taste of the major trendy directions and presented in this are presented in this short talk, and this follows with some examples. For example, the well-known radiocarbon amongst the methods deployed for dating organic materials are really intriguing based on the physical, chemical, and biological mechanism. Radiocarbon is one of them, which continually is improved since its discovery, for which physical chemist Willard Libby got the Nobel Prize in 1960. Carbon-14 is produced from solar and cosmic neutrons, heating atmospheric nitrogen here, which as CO2, carbon dioxide, is distributed throughout the atmosphere, the biosphere, and the oceans. And these are referred to collectively as the carbon exchange reservoir. The different elements of the carbon exchange reservoir vary in how much carbon they store and in how long it takes for the C14 generated by cosmic rays to fully mix with them. This is the principle of radiocarbon dating. Upon the termination of this carbon exchange with an organism, a plant or an animal, the existing C14 decays with a half-life of around 5,730 years, decreasing from, say here, atoms N0 to atoms N capital by time, and thus the time or the age equation is easily computed. However, for this method, the variation of C14 to C12 ratio in different parts of the carbon exchange reservoir means that a straightforward calculation of the age of the sample based on the amount of carbon-14 it contains will often give an incorrect result. So there are several possible sources of error that need to be considered here. The errors are of four general types of variation. The variations of C14 to C12 in the atmosphere, both geographically and over time. Second, the isotopic fractionation. Third, the variations of C14 to C12 in the different parts of the reservoir, and also contamination. Here we present a simulation of C14 dates with probabilities with upper and lower boundary. In fact, here we show two heights of simulation on the left and on the right. In the left, from 900 to 1100 BC, the ghosted distribution, you can see here, in grayscale, represents the standard and model calibration date. And the dark gray black distribution is the calibrated one here. Then at the 68 and 95% the probability age range is computed. At the right hand side here, we have a simulation of a sequence of events in the same site, assumed to be, for example, for the period 1000 and 1200 AD. In this simulation, we include no dating information, but only the order of events, older and younger. The simulation of a series of 10 here, C14 dates, you can see, is assumed to come from the same period. The plot on the right, thus, it shows a kind of resolution what might expect to get from such a Bayesian model, as it is called, in this period, with uncertainty terms of the carbon-14 dates of plus minus about 25 years. Taking into account all above mentioned sources of error, the yearly improvement of the calibration curve due to the C14 variation in atmosphere and the subsequent introduction to organic species, the representation of errors is made by what we call the Bayesian modeling. However, here we have to be very careful that in the final statistical error, which we give to archaeologists, is not only the counting statistics, nuclear counting statistics, neither the calibration, but other inherent sources which one has to be very careful in critically assess any age result. An application of this radiocarbon dating by AMS, acceleration mass spectrometry, which dates very minute weight of samples, is the dating of olive tree in just a moment, in Santorini, and also the Ojiman, which is the well-known, human that was found in Alps, and the dating was around 3,300 to 3,100 BC, This is the time of that early archaeometallurgy in Europe started. The application of also the Akrotiri Thera, the eruption which occurred in 2nd millennium BC and was the main cause of destruction of Minoan civilization. Here is the dating of an olive tree, olive branch. It was 1600 to 1627, although still there is a debate between 1550 and to 1600 BC, for this dating event. The Turin shroud is the dating of Turin shroud. Finally, it is not the the linen textile that was covering Jesus Christ body after death, but it was finally dated to 14th century AD, and that thus has solved this mystery. Although the Catholic Church said to the believers that you can believe whatever you like, the science says that, but you can believe whatever you want. The Lascaux cave in France, the famous rock art painting in Lascaux was dated by C14. It was actually the black pigment you can see here, which was charcoal, and that determined the age of the mural painting to 1500,000 years. There are around 600 rock paintings and 1500 engravings in this Paleolithic site. It was interesting to see that the various ochres, used as pigments by the Paleolithic painter, to make this art wall, finally could be dated by this black, as I said, color, which is charcoal. The other important method of dating is the luminescence, focused on inorganic materials. You can see metal or lithics, stones, rocks, etc., and ceramics, of course. This is the stone monuments, the masonry, the walls, rock of art, sculptured stones can be dated by the version of luminescence, which is called surface luminescence dating method. There are two versions, the thermoluminescence and the optical stimulated luminescence. Initially was developed to date, burned material of ceramic fabric, and eventually was used to date stone monuments as well. Other monuments that could be dated by luminescence, and this is recently actually very popular, is to date the rock art engravings in the walls, like this here in Chinese rock art in Mongolia. Here is the one of the equations that can be used to date, rock art dating. There are some other versions as well. Now, questions like where from, analysis and provenance of raw materials and technology arise for ceramics, obsidian tools, marble, and metal fights. All this can be analyzed by particular methods, either as meteorological analysis or chemical analysis, and finally to provide an answer regarding not only technology, but also the origin of the raw material. Physical methods used are various, actually, from all the fields of physics, chemistry, geology. One can get a technique or a physical or chemical a mechanism which can be used for analysis or dating, in cultural materials. So X-ray fluorescence, X-ray diffraction, scanning electron microscopy, microanalyzers, lead isotopes, mass spectrometry, ESR, etc. The ceramics is a case study. Because ceramics can be found scattered everywhere in all archaeological sites. And this is the first spotted, tangible material that the archaeologists, acquire and may have a first impression about the dating of the chronology of the site which has been covered underground. It's a case study, ceramics, because it's frequently met material, as I said, after the Neolithic period around 7,500 BC. I mean, 9,000-10,000 years from today. The diversified constituents of the ceramics can be identified, as I said, by various analytical techniques, chemical and mineralogical characterization, as well as classification, provenance, production technologies, economic exchanges, trade routes, etc. The meteorological and also metrographic composition, organic archaeometric approach of coatings, recognition of the geological sources, and all this provides solutions to the finally synergic instrumental strategy in a complementary way, integrated approach of analytical techniques, and a complete map of the protection centers of the objects and of their transfer. For petrographic analysis, for example, electron probe microanalyzer and scanning electron microscope with X-ray diffraction in ceramics is used. For example, here is X-ray maps for different elements: calcium, sodium, phosphor, potassium, which shows zonations and in a large grain, mineral grain, large grain, in relation to the adjacent matrix, as well as microphotographs. These are useful and necessary information towards the provenance and identification of clay sources. Advancement also has been made in the field of genome project of ancient DNA reconstruction data, which help understand the mobility, ancestry, and globalization of ancient societies. An example here is the origins of the Bronze Age Minoan and Mycenaeans in relation to the surrounded areas, cultures which have puzzled archaeologists and anthropologists for more than a century. It has been shown that Minoans and Mycenaeans were genetically almost similar, having at least 3/4 of their ancestry. You can see here in the red circle the data on Aegean for here, and with respect to the surrounded, as I said, cultures. So there are almost similar and having, as I said, 3/4 of ancestry from the first Neolithic farmers of the mainland Greece, Aegean and the Western Anatolia, so around the Aegean, basin. And most of the remainder come from ancient populations related to those from Caucasus, here Caucasian, and Iran. A new study which is in press, in Science, we have reinforced and strengthened actually this result with much more data and gives a final picture of what I said right now. Last but not least, the research direction of astronomy called Archaeoastronomy is also increasing in novel findings concerning ancient beliefs, religion, festivities, determination of time, and everyday activities. Here, for example, is the Vega, the brighter star. You can see here. The bright star of Lyra, the constellation, which rises straight in front of the Temple of Apollo in Delphi, followed by Swan, Cygnus. The appearance of the favorite constellation of God Apollo orbit throughout the Delphic night in 9 months over the year. The other 3 months, this bright star and the constellations are not seen in the night sky of Delphi. Of course, the orbit exists, but during the day, and this symbolizes the absence of Apollo to the land of Hyperboreans, 3 winter months. It was this 3 winter months period that the priestess, Pythia, did not deliver oracles because the spirit of God was absent. So the recurrency of giving oracles was determined, at the end of this 3-month period, but the start of this 3-month period and the end of this 3-month period was not known how the learned priests could determine the exact timing. So that was found to be through the appearance and disappearance from the Delphic night sky of bright constellations, which are the favorite to God Apollo, as I said before. This kind of archaeoastronomical interpretation is connected to the myth of Apollo visiting the land of Hyperboreans during the 3 winter months, when Pythia, the priestess of the sanctuary of the temple, did not deliver oracles. Also, we have another archaeoastronomical application to China, not only Greece, but many other important countries have used, guided by the starry night. Tomb orientation in China is a serious matter in mortuary ritual. The tomb is the home of the dead, and the posthumous journey to the center of the supernatural world is to report their arriving in order to live a better life in the other world. So by contextualizing the predominant orientation of asymmetry, we may find the religious belief of the afterlife. In the case of Guosymmetry, in 770 to 660 BC in China, most burials were aligned to the deaths of the North Star, which is deviated to the east. And such an orientation is definitely pointed to the North Polar Star, which is the abode of the Supreme One in later religious beliefs of the heaven. Placing the dead and their head towards north is a common practice in Xia, Shang, and Zhou dynasties, the most important dynasties in China. And the change of deviation from west to east coincides with the change of the North Polar Star to the Thuban, from Thuban to Kochab, which is the names of bright stars. So here you can see what I was talking. Here is the skyscape of northern stars for Guo, made by Stellarium, the software. The A is 600 BC and the B is 800 BC. The positioning of these bright stars I was talking to you about, the Polaris, the Kochab, and the Thuban, and then how it moves, to the position, and this shift of the bright stars leads to the people to orientate the top towards this direction, which is indirectly also a chronological tool. Okay, so here is the representation of how it looks, in the like in the sky, the Polaris and the Big Bear, the Ursa Minor. So as you can see, the three bright stars of Polaris, which is the Ursa Minoris, the Thuban, which is from the Draco, the constellation of Alpha Draconis, and the Kochab, which comes from the Ursa B, is the beta star of Ursa Minoris, as well as astronomical data of azimuths, declinations, etc., give this kind of picture. So the archaeometry, our stomach, as I said at the beginning, and I close with that, which essentially this is, exactly this branch, the science, technology, engineering, mathematics applied in arts and cultures. Is studying the past archaeometrically or new technologies in arts and cultures. What is the use, for example, for the present and the future? I mean, just collecting data of analysis regarding ancient societies, so what for, But if one delves into this information in a multi-level information, multi-level information, multifaceted, several questions and respective answers can be emerged, from this interdisciplinary and multi-scientific subject. Questions regarding the holistic information regarding the holistic study of ancient societies, or the fact that history is repeated, or geophysical phenomena and physical phenomena are repeating as well in the past, and what existing in the past, existing in the present, and will continue in the future. We may know also the frequency of occurrence. This is we take information regarding our evolution, the cultural evolution. Whatever problems we face at the present, people in the past have been faced. So in a comparative way, one can make some stochastic, and philosophical thinking, but as a stasis, as a way of living, and this certainly provides us with very useful and meaty data, how to live in the present and how to plan our future. So the archaeometry, this subject, has interdisciplinarity. It retains the memory of our past, and in this remote past, we can meet our future, and certainly, gives us ecumenical values, because through arts and cultures and properly studied, people understand better themselves and apply, intangible principles of peace, of love, of coexistence, etc. So I could say, without exaggeration, that archaeometry is the heart of the present, in which past and future meets. Thank you.